Welcome back to the deep dive. So if you've ever worked in a dynamically typed language, you know that freedom, right? The flexibility.
Oh, absolutely.
Yeah.
But that flexibility can be a double-edged sword.
Right. It's an absence of any kind of structural guarantee. I mean, when you pass an object to a function, how do you know it has the methods you actually need?
You don't. And that lack of structure leads to brittle code, which is exactly why we're diving deep into abstract base classes, or ABCs.
This isn't just theory, is it? This is about architectural enforcement.
It's all about enforcement. ABCs are the mechanism that turns a flexible class definition into a mandatory enforceable contract.
So the mission today is to figure out how these classes create that abstraction and why that structure is so important. We're looking at classes that are, well, intentionally incomplete. They set the rules but don't implement the features.
Exactly. The sources call them non-concrete. An abstract class is a mandatory template. It's missing key details. You can't ever create an instance of it directly.
Its whole purpose is just to be inherited.
Sole purpose, yeah. It sets the interface. And then the child classes, the concrete classes, they must fill in every single blank that the abstraction defined.
And we might hear this parent class called different things, right? Like a base class or a super class.
Same idea. The core function is the same. It ensures that when a derived class is finally created, it has followed every rule in the blueprint.
And today we're going to get into how they're created, how they work with type hinting and collections, and even how they let us redefine Python's own operators. Okay, let's unpack this enforcement mechanism.
Let's do it.
So to ground this, let's start with a simple example. Think about defining a generic media player.
Or a perfect abstraction.
It has these universal functions, just play, pause, and stop. It has to define those capabilities, but it can't actually do the work itself.
You can't, because the media player abstraction doesn't know anything about the format. Is it a WMA file?
Mm.
An OGG file? A stream?
Right. So each of those specific file formats becomes the concrete implementation.
Exactly. And the abstract class enforces the rule. If you want to call yourself a media player, you must implement a play method. No exceptions.
And what I found fascinating from the sources is just how lightweight that abstract definition can be. I mean, in the code, for those abstract functions, you don't even need any logic.
No.
You can just use the keyword pass or an ellipsis or sometimes just a doc string.
It's just a signal. It says, I exist as a concept, but someone else needs to do the actual work.
Once you get that principle of enforcement, you start seeing it everywhere.
And that leads us straight to collections.abc. This one module provides the abstract-based definitions for pretty much all the foundational Python containers you use every day. Your list, your dict, your set.
Wait, so when I just create a simple list, I'm implicitly using an object that has to follow this massive enforced contract.
Absolutely. And there's a whole hierarchy.
Yeah.
The most general abstraction is just a container. All it does is support membership testing. You can ask, is X inside me? That's it. Then you add sized for length checking. And finally, you get to the collection abstraction, which combines both of those and adds more.
That seems almost overly granular. I mean, why is it so important to break down something as simple as a list into these tiny abstract pieces like container and sized?
Because it gives programmers maximum flexibility without breaking consistency.
Yeah.
Say you want to build a custom data structure like a thread-safe cache.
Okay.
You might only need it to check for membership and length.
Yeah.
So you can just inherit from container and sized without being forced to implement other methods like iteration, which collection might require.
Ah, so you only take on the contracts you absolutely need.
Exactly. ABCs provide the toolkit for building these incredibly custom structures while guaranteeing they still behave like standard Python objects.
Yeah.
And that's key for integration.
That makes a lot of sense. So let's take that idea of structural enforcement and apply it to a bigger architectural challenge.
Sure.
What if we need to build a custom container? Something like an immutable mapping, a lookup object that's like a dictionary, but you can't change it after you build it.
How do we make sure our custom class plays nicely with all the existing Python tools?
Yeah, how do we do that?
Well, we have to adhere to a protocol. And this is really the concept behind that famous duck typing idea.
If it walks like a duck and quacks like a duck.
It's a duck. If it has the right methods, Python treats it as if it were the standard type. The protocol just defines what those shared methods have to be. ABCs are what formalize it.
And the sources show that for this custom mapping, the constraints can get pretty technical, especially with type hinting. What does this immutable mapping have to look like?
We specify two things. First, the key type has to be comparable,
Comparable meaning?
meaning the keys must allow for comparison, which implies they can be ordered. And second, the value type can be, well, any object.
Hang on a second. Why do the keys have to be comparable and ordered? I mean, a standard Python dictionary doesn't require that at all. It's built on hashing.
That is a fantastic point, and it gets right to the heart of the trade-off we're making here.
So this is an imposed architectural burden.
It's a deliberate choice. We are choosing an architecture that prioritizes efficiency over the simple speed of a dictionary lookup. If we require the keys to be ordered, we can use a lightning-fast binary search instead of just iterating through the list.
Okay, so we're trading flexibility for speed. We're choosing O log n search time over a potential ON.
Precisely. And to maintain that order efficiently, the source material focuses on using Python's bisect module. This module makes sure that when we insert a new key-value pair, the list of keys stays sorted without us having to resort the whole thing every time.
And the sources highlighted two specific functions, bisect left and bisect right. They seem really subtle.
Yeah, the nuance is really only required if you're handling duplicate keys, but for data integrity, it's critical.
So what's the difference?
Bisect left gives you the insertion index, but if the item is already there, the new one goes before any existing entries.
Okay, so it pushes everything to the right.
Exactly. It finds the leftmost possible spot for insertion.
So bisect right must be the opposite.
Right. It returns the rightmost insertion index. It places the new entry after all existing duplicates. So if you have a list of 10, 10, 10, bisect right puts the new 10 at the very end.
And that distinction is how you'd maintain, say, a strict chronological order if you had items with the same timestamp.
That's a perfect use case. It gives you that fine-grained control over your data's structure.
Okay. We enforce the structure with the ABC. We enforce the efficiency with comparability and binary search. And speaking of efficiency, we tease the big O notation. So why is O log n for binary search so much better than a linear search?
Well, in short, it's because the time it takes doesn't grow linearly with the number of items. If you double the size of your data, you only add one more step to the search process.
Just one.
Just one. So a list of 1,000 items might take 10 steps. A list of 1,000,000 items only takes about 20 steps. That logarithmic speed is what you lock in when you commit to the discipline of an ordered ABC structure.
That is a huge payoff. So if we accept that discipline, what are the essential steps for actually implementing one of these things, according to the sources?
Okay, so there are 4 key steps. First, don't start from scratch. Find an abstract class, probably in collections.abc, that already does most of what you want.
Step 2 is to identify what's missing.
Right. You use the help docs, or even look at the source code, to see which abstract methods are still undefined.
And third, you subclass that abstract class, and this is where that contract gets enforced.
This is it. You must implement every single required method. If you miss one, just one, Python will throw a type error the second you try to create an instance of your class. The contract is ironclad.
And the final step, step 4, is testing. The sources specifically mention MyPy and Unitest. Why both?
Because they're testing 2 different things that are both essential to the contract. MyAppy is for static type checking. It checks your method signatures, your input types, your return types to make sure they align with the protocol.
It checks the structure before you even run the code.
Exactly. And Unitest checks the function at runtime. It confirms that the logic you actually wrote for those methods works correctly.
So one checks the signature, the other checks the behavior.
Together, they confirm you've successfully fulfilled the contract of the abstraction.
And this idea of enforcing behavior, it's not just for data structures, it's perfect for modeling rules. Let's move away from containers and look at something like games. We can use ABCs to model the concept of polyhedral dice.
That's a classic example. The abstract class defines what a die is. It must have a method to roll, and it has to have a number of sides.
And the concrete classes are the D4, the D8, the D12, the classic D20.
Precisely.
But the sources went way deeper than that, and they applied this to a full yacht dice game simulation. This shows how an ABC can define and enforce the entire metastructure of the game itself.
It does. If we define the game structure as an abstract class, we can define the core rules that must be true for any version of yacht. For instance, the system has to enforce that the simulation uses 5 6-sided dice.
And that the game consists of exactly 12 turns.
Right. And most critically, the rule that prevents cheating.
The scoring.
The scoring. The abstract class enforces the turn-based limits. So on any given turn, a player gets a maximum of 3 rolls.
No more.
No more. And crucially, it enforces that once a scoring category like Full House is used, the scoring system must not allow that category to be used again. By putting these restrictions in the ABC, The architect ensures any game built on it has safe, mandatory gameplay behavior.
That's incredibly powerful. You're using code to enforce the rules of physics, or in this case, the rules of a game. Let's look at two final applications from the sources. These are really demanding custom data structures that show what happens when you fully embrace these concepts.
Okay, the first demanding structure is the take. It's an advanced double-ended queue. The challenge is to define it by extending something like DEC or another ABC, and then implementing four specific methods. Two are easy: push back and push front.
But the two that make it really complex are push middle and get.
Push middle is the real architectural challenge there. It means the data structure has to know its exact midpoint at all times, which is computationally expensive to keep track of.
And get has to be fast, even at an arbitrary index.
Right. So the ABC forces the programmer to solve these tough performance problems just to comply with the contract.
And the second application, the CD problem, was all about extending built-ins. You have a custom CD data structure that inherits from mutable sequence. But the real magic here wasn't just manipulating the sequence, it was about making it feel native.
This is the massive aha moment. It's operator overloading. So the custom CD class needs to find the intersection of elements, say, the shared songs between two CD collections.
And you could just define a normal method, right? Like jack.findCommonTracks, Jill. That would work.
It works fine, but it doesn't look like Python. It's clunky. The ABC structure lets us implement a special method, and
The one with the double underscores.
that's the one. By defining that method inside our custom CD class, you are effectively overloading the standard Python bitwise and operator. For this class, and now means find intersection.
So instead of that long, verbose method call, you can just write Jack and Jill.
And that's it. It looks clean, it feels intuitive, and it makes your custom structure immediately readable to any Python developer. That ability to integrate new complexity so seamlessly into the existing language syntax, that's structural programming at its finest.
Wow. So, to synthesize this whole deep dive, abstract base classes are this powerful, enforced blueprint. They guarantee consistency, whether you're trying to make a structure faster with binary search or model the complex rules of a board game.
Or even making advanced data operations feel simple and accessible using operator overloading.
They're the foundation of predictability.
They are. They ensure structure before execution, forcing developers to adhere to standardized protocols so that every piece of the system, even the brand new ones you invent, integrates beautifully.
Now, our sources mention one more concept right alongside ABCs, but they didn't really give it any attention: metaclasses.
Right. We spent this whole time focused on how abstract base classes define the structure of the object, what methods the concrete class has to have.
But a metaclass, that works at a completely different level.
It does. A metaclass is the mechanism that creates the class itself. It defines the structure of the class.
Okay, I'm not sure I follow.
Well, if the ABC says, this class must have a role method, the metaclass can say, any class that I create must have documentation for all of its methods. It's a rule about the class, not the object.
So the provocative thought we'll leave you with is this: how might metaclasses be fundamentally related to ABCs? What kind of powerful new abstractions could you unlock when you control not just the object structure, but the definition of the structure itself? When you control the engine that creates the blueprint, what new rules can you enforce?
Something to mull over until our next deep dive.